Alright, in this video we're going to look at a little bit of terminology associated with polynomials. We're going to get into a little bit of long division and synthetic division with polynomials. So this is going to be some skills that we're going to do a little bit of practice of, and then we're going to apply that in a little bit later sections here. We'll also look at constructing polynomials given some certain criteria, like what kind of roots or zeros that they have. So a little bit of terminology. A coefficient of a term is the factor attached to it. The degree of a polynomial is going to be the largest exponent, provided that it's completely expanded out. If it's factored, then it's a little trickier to figure out what the degree is. The leading coefficient of a polynomial is the coefficient on the term with the largest exponent. And then the last thing, there's certainly other things, but the last thing we're going to mention here is an nth degree polynomial will have at most n roots. And so a real basic example we could say is, x squared minus 13x plus 36 is equal to 0. That's going to factor into x minus 9 and x minus 4 equals 0. So your roots or your zeros are 9 and 4. Later on we're going to set up a little chart where we'll have our root and then our factor. So notice one thing, that if 9 is the root, x minus 9 is the factor, and if 4 is the root, then x plus 4 is the factor. And so we'll continue that idea near the end here. So we're going to move on to the next page, and we're going to identify the coefficient and degree of each term, identifying the leading coefficient and the degree of the polynomial, state the maximum number of zeros. So I'm not going to write down all those instructions, but I'm going to make a table to kind of summarize that information. So we're going to look at, I'm going to call our polynomial p of x, which is going to be negative 1 plus 3x squared plus 5x to the 17th, and then minus 29x squared. And I'm going to go ahead and make a factor, not a factor chart, but a different type of chart or table. So we're going to do term, degree, and the coefficient. Terms are separated by addition or subtraction signs, so the terms are negative 1, 3x squared, 5x to the 17th, and minus 29x squared. And as a note here, or recall, that b to the 0 is going to be equal to 1. So if I say negative 1 times x to the 0, that's negative 1 times 1, which is negative 1. So that helps us out. The degree is going to be the, on the term is going to be the exponent on the x. So if it's a constant, the degree is going to be 0. And you can see for those other terms there, the 3x squared, the 5x to the 17th, and the minus 29x squared, they all have an x that we can explicitly see, exponents being 2, 17. Oh, did I write something down wrong? Oh, silly me, I have two squares there. So let's change that up there. Let's just make one of them, because the problem wouldn't be would not be presented this way, where the terms would be the same. So let's go ahead and just change it for 3, just for the sake of variety here. Okay. So we'll go ahead and make that a 3 there, just so we have something that's different. Okay. Now we're going to grab the coefficients. So our coefficients are going to be minus 1, 3, 5, and negative 29. The 5x to the 17th, that has the largest exponents. That's going to be the leading term. So the leading coefficient is going to be 5. And our degree is our largest exponent, which is 17. So this will have a maximum number of zeros being 17, or roots being 17. Okay, a big polynomial. So the maximum number of zeros would be 17 for this one. Okay, so we're going to look at another one, part B, and this one is actually factored out, or not? It's factored, and so there it is. And so it's a little harder to tell what the degree is. Now, if I imagine I expand that out, I'm going to have an x cubed times an x cubed, so that's going to give me an x to the 6th. So that's what the degree is going to be here. Now I can go ahead and expand it out though, so I'm going to go ahead and mention that the degree here is going to be 6. 2 times 3 will be 6. Okay, so we'll go ahead and expand it out. So the x minus cubed to the 5th squared means 2 of them. And so we'll go through and we'll FOIL that. And then distribute the minus 2. Okay, and we'll make our little term, degree of each term, and then the coefficient of each term. Then we can use that to kind of just break everything down and then identify what the leading coefficient is and the degree of the polynomial. So there's our terms. Degrees are the exponents. Remember, the constant has degree 0. And the coefficients being minus 2, 20, and negative 50. The negative 2x to the 6 is the biggest exponent, so that's our leading coefficient. This is a degree 6. And so for a degree 6, that means the maximum number of zeros is going to be 6. Okay. So we're going to do a little bit of a review of long division of polynomials. Sorry, not polynomials, of just numbers, and we're going to apply that to polynomials. Okay, so if I want to do 59 divided by 3, 59 is called the dividend, and 3 is called the divisor. And then we set it up, divisor on the outside, dividend on the inside. So we have 3 into 59. So 3 goes into 5 once. 3 times 1 is 3. Well, then we'll subtract. 5 minus 3 is 2. Okay. And then bring down the 9. 3 goes into 29 9 times, and 3 times 9 is 27. Subtract, and we get a quotient of 19 and a remainder of 2. So 59 divided by 3 is 19 plus 2 over 3. So quotient plus the remainder over the divisor. Let's do one more example. Let's go ahead and do 102 divided by 3. So 3 into 102. 3 does not go into 1, but it does go into 10 3 times. 3 times 3 is 9. Subtract. Bring down the 2. 3 goes into 12 evenly 4 times. We get a remainder of 0. So 102 divided by 3 is 34. Now, because we got a remainder of 0, that means 3 is a factor. That means it divides in evenly. So 3 is a factor of 34 of 102. And 3 is not a factor of 59 because we did not get a remainder of 0. Okay, so the only time it's going to be a factor if it's a remainder of 0. Okay. All right, so for polynomials, we can do the same thing. We can take a polynomial p of x and divide it by a non-zero polynomial g of x, and that's going to give us a quotient polynomial plus our remainder polynomial over our divisor polynomial, where the degree of the remainder is less than the degree of the divisor. So let's see if I can put that up there. Okay. So the polynomial p of x divided by a non-zero polynomial g of x is going to be equal to a quotient polynomial q of x plus a remainder polynomial over the divisor polynomial, where the remainder degree is less than the degree of the denominator. Okay, so we're going to go ahead and apply this, and I'm going to write down kind of pretty much all the possible steps that you can. A lot of it you end up doing in your head, but we're going to write it all out, try to be real thorough. Okay? And we'll do 2 examples of long division. Okay, so we're going to look at dividing x to the 4th minus 3x cubed minus 9x squared plus 6x and minus 280, and we're going to divide that by x plus 4. So the divisor goes on the outside, and the dividend goes on the inside. So we're going to write that whole thing out, that big long mess with polynomial. Okay, and like before, we're going to ask ourselves, so when we were doing 3 into 59, we want to know how many times did 3 go into 5, and that was once. So here we're going to ask ourselves the same question. How many times does x go into x to the fourth? So another way of doing that is x to the fourth divided by x is x cubed, okay? And then, like when we did the 3 into the 59, okay? 3 went into 5 once, and then you did 3 times 1, which was 3, and then you're going to subtract. So we're going to do the exact same thing, but what's a little bit different is we have x plus 4. So we're going to have a little bit extra when we're doing the multiplication. Okay, so we figured out it was x cubed, and so we'll do x cubed times x plus 4. That's going to give us x to the fourth, and then plus 4x cubed. Okay, so x goes into x to the fourth, x cubed times x cubed is x to the fourth, and 4 times x cubed is 4x cubed. And then we're going to go ahead and subtract like we do with regular long division. But what I like to do is I like to distribute the minus sign and change the signs. I'm less likely to make an error. That's usually what happens is there's a sign error somewhere along the way. So change the signs. Minus 7x cubed is the difference with the x cubes. The way this is constructed, these should always cancel out. If they don't, then that means you have made some sort of error. Okay, so minus 3x cubed plus a negative 4x cubed is minus 7x cubed. Bring down the next term. Sometimes you might have to bring down the next 2 terms, or maybe you'll have like a term you skipped over that you'll have to bring down. Just kind of depends on the situation. Okay. All right. So we're going to play the same game again. So x times blank is minus 7x to the third. So we can spell that out for you. Minus 7x cubed over x is minus 7x squared. And then we'll do minus 7x squared times the x plus 4. Okay, so that's our scratch work. Alright, so x times minus 7x squared is minus 7x cubed. And then positive 4 times minus 7x squared is minus 28x squared. And we'll subtract. Change your signs. 19x squared, bring down the next term. And then we do it all over again. So how many times does x go into 19x squared? Let's find out. It's going to be 19x. 19x times x plus 4 is going to be 19x squared plus 76x. Okay, so x goes into 19x squared, or x times blank is 19x squared, that's 19x. X times 19x, 19x squared. 4 times 19x, 76x. Subtract, change your signs. Negative 70x, bring down the last term, minus 280, and play the game one more time. Minus 70x divided by x is minus 70. And then we're going to multiply minus 70 times x plus 4. And that'll give us negative 70x. And minus 280. So x times minus 70 is minus 70x. 4 times negative 70 is negative 280. Subtract, then change the signs, and we get a remainder of 0. So there's our remainder. And we also have our quotient on the top there. And because our remainder is 0, that means that x plus 4 is a factor of this giant polynomial, x to the fourth minus 3x cubed minus 9x squared plus 6x and minus 280. So we're going to be really interested in what is going to be a factor in the next section or two in our class here. Let's do another example with long division, and then we'll show you a little bit of a shortcut for dividing by linear factors or linear divisors. Okay, so this time we're going to look at 16x to the fourth and a plus 40x cubed minus 8x squared plus 18x minus 255. I'm going to divide that by 2x minus 3, and we'll go ahead and set up our divisor and our dividend. and we're going to do the same thing we did in the previous example. So how many times does 2x go into 16x to the fourth? That's 8x cubed. Okay, so take 8x cubed and multiply it by the 2x minus 3. And so that's going to give us the 16x to the fourth and minus 24x cubed. There's your 8x cubed, and then multiply 16x to the fourth minus 24x cubed. Subtract, change the signs, 64x cubed, bring down the next term, and do it all over again. 64x cubed divided by 2x is going to be 32x squared. Multiply the 32x squared times 2x minus 3, be 64x to the third, and minus 96x. Okay, so there's your 32x squared, 64x cubed, and minus 96x squared. Subtract, change the signs, and we're left with 88x squared. Bring down the next term, and do it all over again. 88x squared divided by 2x is going to be 44x. 44x times the 2x minus 3 will be 88x squared, and I'll fix that in a second, and minus 132x. 44x goes up there, 88x squared, and minus 132x. Subtract, change the signs, and bring down the negative 255, and do it one more time. So 150x divided by 2x is going to be 75, and then we're going to take the 75 times the 2x minus 3. That'll give us 150x and minus 225. Here's our 75. 75 times 2x, 150, and then minus 225. Subtract, change the signs, and we get a remainder of negative 30. So we got our quotient and our remainder. Because our remainder is not 0, we can say that 2x minus 3 is not a factor. It does not divide in evenly. So it will only be a factor if it divides in evenly. Okay? And so those are two examples of long division. Certainly there'll probably be other examples that you can see on YouTube. Maybe just do a little bit of Google of long division of polynomials if you're looking for more examples, or you can look at our textbook. I think I might have another video somewhere out there of another example or two of long division of polynomials. All right, so next thing we want to look at is the synthetic division. And so synthetic division is kind of like a shortcut, and it's for the divisor in the form of x minus c or x plus c. Okay, so if you're in the form x minus c or x plus c, you can use synthetic division. It's a lot faster, and that's what we'll use mostly when we start getting into some of the theory, when we're doing the factor theorem and the remainder theorem and the rational roots theorem. All of those, you can use synthetic division, and it makes the process a lot faster. So one of the things to notice, if it's an x minus c, notice that when we're going to put the opposite out there, a positive c. Or if it's an x plus c, we're going to put the opposite out there. It's going to be a minus c. So we're going to do two examples, kind of get the hang of it. It's not real bad once you kind of notice the pattern here. Okay, so we're going to look at, I think it's the same problem that we did at the beginning with long division, but we're going to do it with synthetic division. So there's our dividend, and there's our divisor. So first thing to know is it's an x plus 4, so we want to use the opposite side, and we want to use a minus 4. And then we're going to grab the coefficients of our polynomials, so 1x to the fourth, minus 3x cubed, minus 9x squared, plus 6, and minus 280. So what it does is it relieves us from having to deal with the x's for the time being. Okay, so we're not gonna worry about that, and we'll get them back when we're all done. Okay, so the way this works is whatever that first number is inside, that being the 1, we're going to bring down the 1. Okay, and then we're going to multiply. The outside number, negative 4 times 1, is negative 4. And then we're going to add negative 3 times negative, let's start over. And then we're going to add negative 3 plus negative 4 is negative 7. and then we're going to multiply. Negative 4 times negative 7 is 28. And then we're going to add. Negative 9 plus 28 is, I think it's 19. And then we're going to multiply. Negative 4 times 19 is negative 76. And then we're going to add 6 plus negative 76, negative 70. And then we're going to multiply one more time. Negative 4 times negative 70 is positive 280. And then we get a remainder of 0. Okay? So we're all done. We stop when we're at this last number. Okay? And now what do we got? We got a remainder. And then we got a constant. And then the next would be x squared, x cubed, and if there was more numbers, you just keep increasing those exponents. Okay? So we have x cubed minus 7x squared plus 19x minus 70 is our quotient, and our remainder is 0. Okay? And so that's exactly what we should have gotten with the what problem was that? I think it was the first problem we did. We got the same thing. Or maybe it was number 2 or something like that. Yeah, it was number 2 that we got that same quotient and remainder there. So that's good. Okay, we're going to look at one or two more of this synthetic division. So number 5 here, we're going to do x to the 4th minus 3x cubed minus 12x minus 14, and then we're going to divide that by x minus 4. Now, when we took the 102 and divided it by 3, you do have that placeholder 0 right here, and it looks like a person, doesn't it? Anyways, you have that placeholder 0, and that's important. Not only when we represent the number, we don't represent it as 12, we represent it as 102, so that placeholder is important. And a similar argument or a similar thing happens here. Notice that you don't have an x squared term here. So what we're going to do is we're going to put a placeholder 0 there. If we don't put it there, then the synthetic division doesn't work. You can kind of get away with it with long division. I don't recommend it. Things don't line up. So if you're missing a power of x, go ahead and put a placeholder 0 in. Okay. Now the opposite of the x minus 4, the divisor there is 4, and then coefficients 1, negative 3, and we didn't have an x squared, so we'll put that placeholder 0 in. The minus 12 for the x and the minus 14. Okay. So 1x to the 4th minus 3x cubed plus 0x squared minus 12x and minus 14. Alright, so we'll go ahead, bring down that 1. 1 times 4 is 4. Add. Minus 3 plus 4 is 1. Multiply. 4 times 1 is 4. Add. 0 plus 4 is 4. Multiply. 4 times 4 is 16. Add. Negative 12 plus 16 is 4. Multiply. 4 times 4 is 16. Add. And you get a remainder of 2. So there's your remainder, your constant x squared, and x cubed. So we can say that this is 1x cubed plus 1x squared plus 4x plus 4 plus your remainder of 2 over the divisor of x. It's not x minus 2. Sorry, it is x minus 4. And because our remainder is not 0, we can say that x minus 4 is not a factor. Okay. All right, we're going to look at a little bit more. We're going to say ask, is x minus 9 a factor of x squared minus 13x and plus 36? And we'll use synthetic division. So our divisor is going to be x minus 9. The opposite of the minus 9 will be plus 9. Coefficients on x squared minus 13x plus 36 are 1, negative 13, and 36. Bring down the 1. 9 times 1 is 9. Negative 13 plus 9 is 4. Is not 4, it's negative 4, pardon me. 9 times negative 4 is negative 36, and add, we get a remainder of 0. Because we've got a remainder of 0, we can say, yes, this is a factor. And if you remembered at the very beginning, we did factor this. and it factored into x minus 9 and x minus 4. So you do see it as a factor right there. Here's your remainder, here's your constant, here's your x. Notice that your quotient is x minus 4, which is exactly the other factor there. Okay. All right, for the last part of the video, we're going to be changing gears a little bit. We're going to be looking at constructing polynomials. So all this division thing and asking about whether things are factors, that's kind of decomposing or deconstructing, not decomposing, if we don't want to do that, deconstructing polynomials here, okay? All right, so some stuff here. Complex conjugates. The conjugate of a plus bi is a minus bi. Notice the a and the b are the same, other than we have a plus or a minus, so the sign is different for the conjugates. Recall that I squared is a minus 1. And then we have a property. If we multiply a complex number in this conjugate, that being a minus bi and a plus bi, you can go through the details, and that gives you a squared plus b squared. So there's your sum of squares. You can certainly use that when you're expanding polynomials as a nice little bit of a shortcut. And then we have a theorem that says that complex roots, or zeros, however you want to refer to them, come in conjugate pairs. Okay, so we're gonna do an example of that property there. So let's say we're given that negative I, 2 plus 5i, 3 minus 2i, and 5 are roots or zeros of a polynomial p of x. And then from this information, can you tell us what some other other roots would be, using the fact that complex roots come in conjugate pairs? So what are some of the other roots of your polynomial p of x? Okay. So the complex conjugate of so if we have a plus bi and a minus bi, those are complex conjugates. So the complex part is the only thing that changes sign. So if we have a negative I would be the complex conjugate of that. 2 plus 5i's conjugate would be 2 minus 5i. And 3 minus 2i has a conjugate of 3 plus 2i. Okay, and then we got some definitions here. The multiplicity of a factor is the number of times it appears in the factorization of a polynomial. The multiplicity of a root, or zero, is the multiplicity of its corresponding factor. So we're going to use this idea for constructing a couple of polynomials here. Okay, so we're going to construct a polynomial with roots of 1, 2, and minus 4. So we're going to make a little table. We're going to have the root, the factor, and then the multiplicity. Now, there was nothing stated about the multiplicity in the instructions, so if they don't say anything about the multiplicity, we assume that the multiplicity is going to be 1. Our roots are 1, 2, and minus 4. And the factor is going to be the opposite, so x minus 1, x minus 2, and x plus 4. Multiplicity is going to be 1 on each one of them. To construct our polynomial, we just string together our factors. Okay? And this polynomial is going to be degree 3. You can add up the, not with the eraser. You can add up the multiplicities, and that's going to tell you what the degree of the polynomial is. So degree 3, degree 4, degree 2, those are all reasonable to actually expand out. So we're going to go ahead and FOIL it. So we're going to FOIL the x minus 1 and the x minus 2 together. And then we'll go ahead and multiply the x squared minus 3x plus 2 times the x plus 4. So, just some routine multiplications. Multiply it all out, combine your like terms, and then you have built your own polynomial that has the given roots that was asked for in this problem. Okay, so we're going to look at another one here, very similar. So we'll speed it up a little bit. Alright, so this time we're going to construct a polynomial with roots of 0 and I. Okay, So we have a root of 0. So the factor of that is going to be a little weird. If 0 is the root, x is the factor. Okay? And nothing about multiplicity, so the multiplicity is 1. I is a root, so x minus I is a factor. Multiplicity is 1. If I is a root, because we know that complex roots come in conjugate pairs, that means also that negative I is a root. And x plus I is a factor. Multiplicity 1. So multiply all those factors together. Okay. And I'm going to multiply the complex conjugates first. That's going to make it the cleanest. You could use my little trick on the previous, maybe it was 2 slides ago. This is going to be x times x squared plus 1 if you use my conjugate trick here. But we'll go ahead and multiply it out. So we'll like FOIL it. So x times x squared plus xi minus I squared. Remember, I squared is negative 1. So this becomes x times x squared. The xi's are going to absorb, and then we have minus negative 1. So that becomes x times x squared plus 1. Distribute that x, and we get x cubed plus x. Okay. We'll do one more. So we're going to construct a polynomial, and so we get a little practice with the multiplicities here. So we're going to construct a polynomial with roots 1, and that's going to have a multiplicity of 3. 0 with multiplicity 2. And negative 4 with a multiplicity 7. We'll make our chart. Root, factor, multiplicity. First root is 1. The factor will be x minus 1 to the third power. X minus 1 to the third power. The next root is 0. Its factor is x, and its multiplicity is 2. So that's going to give us an x squared. And then the final one is root of negative 4. Factor will be x plus 4, and multiplicity is 7, so an exponent of 7. Okay. Now, this polynomial would not be reasonable to multiply it out. This is going to be, if I add up the exponents, it's going to be degree 12. It's probably would not fit on one of my slides here, and if we did attempt to multiply it out, we're going to make a mistake. There's too much computation going on there. So this one here, I would consider leave it in what's called the factored form there, where we don't multiply it all out. Okay. So I think we're done with this one. So we'll see you next time.